Today we will learn what is acceleration, what is the relationship between velocity and acceleration, and how can you determine if an object is speeding up or slowing down. Let's get started. Let's start out by talking about what is acceleration. Acceleration represents the change in an object's velocity each second. So when we talk about this mathematically, we would say acceleration is equal to the change in velocity divided by time. For example, let's look at a case where our initial velocity is 0 or we start at rest, and we have an acceleration of positive 3 meters per second squared. Now, what this means is that if we start out at 0 seconds, our velocity is 0 meters per second. Acceleration tells us how much our velocity changes each second. So, because it's positive 3, that means after a second has passed, our velocity will increase by 3 meters per second. So, after 1 second, we would add 3 to get 3 meters per second. For 2 seconds, we'd add 3 to get 6 meters per second. And for 3 seconds, we'd add 3 to get 9 meters per second, so on and so forth. But this gives you a really good idea of what acceleration does to an object's motion. Now, to calculate acceleration, like I said, when we say the change in velocity, we're going to go ahead and write that as delta v because we're going to look at the final velocity minus the initial velocity. And we're going to calculate that within a given amount of time. And again, this is from last video, so you could either use delta t if t naught is not 0, but because t naught is usually 0, we can simplify our time variable to t. Combining these ideas, we get the change in velocity is delta v, time is t, sometimes delta t, and then our equation for acceleration is a equals delta v over delta t, or a equals delta v over t when t naught is equal to 0 seconds. Now, the thing about acceleration is it can be either speeding up or slowing down. So let's start with speeding up. An accelerating object will speed up when the change in velocity increases over time. So this happens when the magnitude of the velocity, again, magnitude means the number, not the sign. So the magnitude of the velocity is getting farther from 0 meters per second. So, for example, positive 2 to positive 4, we can see that positive 4 is greater than 2. At the same time, if we had negative 2 to negative 4, this would still be speeding up because the magnitude of 4 is greater than the magnitude of 2, regardless of the sign. Now, this occurs when the velocity and acceleration of the object point in the same direction. So you can see the two examples at the bottom of the screen. On the left-hand side, we have an initial velocity that's positive. We add a positive acceleration, so this would be like 2 meters per second plus 3 meters per second. And that would produce a final velocity that's a more positive solution. 2 plus 3 would give us 5. In our other example, we could see on the right-hand side that we have a negative velocity at the start. So that looks like it's about negative 4 meters per second. And then we have a negative acceleration. Let's say it's negative 2 meters per second. We add negative 4 and negative 2. We get negative 6 as our final velocity. Negative 6, its magnitude is greater than negative 2. Therefore, there's an increase. So we can say mathematically that when the magnitude of our final velocity is greater than the magnitude of our initial velocity, then the object is speeding up. In comparison, slowing down is the exact opposite. So an accelerating object will slow down when the change in velocity decreases over time. So this happens when the magnitude of the velocity is getting closer to 0. And in fact, it can go to 0. So, for example, this would be the reverse. So, our initial velocity would be positive 4 meters per second, and our final velocity would be positive 2 meters per second. The magnitude of 2 is less than the magnitude of 4. Or the flip side of that, and the negative side, if our starting velocity was negative 4 meters per second, and our final velocity was negative 2, this would still count as slowing down because the magnitude of negative 2 is less than the magnitude of negative 4. Again, because velocity is a vector, the sign just tells us the direction of motion, not how fast the object is moving. We have to look at the magnitude to tell us how fast. So this occurs when the velocity and acceleration of an object point in opposite directions, meaning they're going to subtract from each other. So in our first case on the left, you can see we have a big positive initial velocity. For instance, we could say it's +6. And then we have a negative acceleration, maybe -3. +6 plus -3 will give us +3. So we can see that there is a large reduction in the magnitude of the velocity at the end. On the right-hand side, we have a person that is running a large negative velocity, maybe -8. Then they have a positive acceleration, so +3, and -8 plus 3 is going to give us -5. So -5 is less than the magnitude of -8. And so, in general, we could say mathematically that when the magnitude of the final velocity is less than the magnitude of the initial velocity, an object is slowing down. Here's a side by side comparison. Speeding up versus slowing down. Velocity increases when it speeds up, slowing down, the velocity decreases. For speeding up occurs when the acceleration and the velocity point in the same direction, so they're going to have matching signs to make a bigger number. While in comparison, slowing down occurs when acceleration and velocity point in opposite directions. So the opposite signs are going to cause a reduction in the magnitude of the motion. So what happens if acceleration is 0? We've looked at every case of speeding up or slowing down. What happens if it's 0? What is the motion of an object that is not accelerating? Well, if you think about it, if there's no acceleration, by definition, there's no change in the object's velocity. So when a equals 0 meters per second squared, we're going to get that v final is equal to v initial. If a is equal to 0 meters per second squared, then our delta v is equal to 0 because we're subtracting the same two numbers. So in this case, since there's no change in the velocity, this means that the velocity is going to stay the same, and the object has constant motion. If acceleration, by definition, is a change in motion, then no acceleration is no change in motion, or constant. Let's go ahead and look at some examples. A plane starts at rest. It speeds up to -140 meters per second in 4 seconds. Solve for the plane's acceleration. Let's go ahead and start out by labeling our diagram. In this case, because our plane is moving in the negative direction, I'm going to say that it starts on the right and it's going to move to the left. So in this case, we're told the initial velocity of our object is at rest. So it's 0 meters per second. Then we're told that it speeds up to a final velocity of -140 meters per second. And this occurs within the time frame from here to here of t is equal to 4 seconds. So first things first, let's go ahead and solve for our acceleration. We know acceleration is equal to delta v over t. In this case, we're assuming t naught is 0. And we have the expanded form v final minus v initial divided by t. Let's go ahead and plug in our values. V final is -140 meters per second minus 0 meters per second divided by 4 seconds. And this simplifies to -140 meters per second divided by 4 seconds. And this simplifies nicely to -35 meters per second squared. Now, it says if the plane maintains a constant acceleration, meaning that our acceleration stays the same, how fast, so we're being asked for velocity, will it be moving 30 seconds after it takes off? Okay, so we're being given some new information here. We're being told that t is equal to 30 seconds. We're being told that we want to have a constant acceleration, so -35 meters per second squared. We still know that our V naught is the same. It starts at rest, 0 meters per second, and we're being asked to find how fast it's going 30 seconds later. So in this case, we're actually solving for a new V final because we're looking at a different amount of time that has passed. Now we can take this equation above our acceleration equation and we can rewrite it to solve for the final velocity. Let me go ahead and write it out. We would multiply both sides by t, and then we would add v naught over, and we will get v final is equal to our initial velocity plus the acceleration times time. Just a little bit of quick algebra to rewrite the equation. Let's go ahead and plug in our knowns. So we know that our initial velocity is 0 meters per second. We know that our acceleration is negative 35 meters per second squared. And we know that the time that the plane has been moving or accelerating is 30 seconds. The first term is 0, so we're just going to simplify this to the other two. So we get negative 35 meters per second squared times 30 seconds. Notice that the seconds will cancel and we'll be left with meters per second. So we're going to get that our final velocity is equal to negative 1,050 meters per second. So we can see that the plane continues to get faster over time. Now let's go ahead and look at a second example to compare. In our second example, a car is driving 30 meters per second. Okay. And it comes to a stop 6 seconds later as it reaches the stop sign. Solve for the car's acceleration. So first things first, let's go ahead and label. This time it looks like we are moving to the right because I have a positive velocity. So my V naught is going to be equal to positive 30 meters per second. And the car comes to a stop 6 seconds later. So from here to here, a time of 6 seconds has passed. Again, I'm going to assume T naught is 0. And at the end, we can see that our final velocity is stopped. So it's going to be 0 meters per second. Now we're going to go ahead and start out by solving for acceleration, which is delta V over T in this case. And then we have V final minus V initial divided by T. Plug our numbers in. We're going to get 0 meters per second minus 30 meters per second divided by 6 seconds. This simplifies to negative 30 meters per second divided by 6 seconds. And we get negative 30 divided by 6, which has an acceleration of negative 5 meters per second squared. So in part B, it says compare the velocities and accelerations in example 1 and example 2. So first things first, I'm going to set myself up with some information so that way we can look at the two problems side by side. So we have example 1, and then we have example 2. And let's compare. We can tell that between V naught and V final, we have negative velocity values, and we also have negative acceleration. In example 2, we can see between V naught and V final, we had positive velocity values and a negative acceleration. So when I'm looking at the two different behaviors, both acceleration are negative. However, example 1 had negative velocities, therefore the plane sped up, while example 2 had positive velocities, so the car slowed down. So when we're talking about acceleration, remember the overall impact that it has is dependent on the direction of motion or the sign of the velocity. Because when we're looking at these two examples, I purposely made sure that both accelerations are negative because oftentimes a misconception with students is that a negative acceleration implies slowing down. That can be the case, but a positive acceleration can also lead to slowing down. The way that you determine which one it is, if it's speeding up or slowing down, you look at the motion of the object. In example 1, the object was moving in the negative direction, so it became more negative, and that is speeding up. In comparison, example 2 was moving in a positive direction with a negative acceleration, which caused it to slow down. So be careful. It's not the sign of acceleration on its own that determines if an object is speeding up or slowing down. It's a combination of which way the object is originally moving and which way the acceleration is taking place. I hope that you found today's video really helpful. Remember that your growth is often found in the journey rather than in the solution. So get out there and go do some physics problems, and I'll see you in the next one.